and I will be doing a short lecture on fused deposition of filled polymers. Um, well, I'm going to cover sort of how fused deposition works for those who don't know, and then how these filaments are made, and then some of the examples that exist. There aren't any commercial examples or industrial as far as specific machines go. You could not put this in an industrial machine. It just wouldn't work. So it's more in the makerscape right now than anything. So um, okay. So how they make the filament first. So obviously when you use a regular polymer filament, you would just extrude it out and then use some sort of feedback to get your correct diameter by pulling it out while it's still in the liquid. So when you add a powder to it, you actually have to typically mix it separately. So you mix it in, say, a twin screw extruder, and then you cut it up again, and then you would put it into a similar extruder that has your feedback loop on it. It's typically a two-step process for to make sure it's homogeneous. And then an example of how an FDM printer works is you basically take this filament and push it through a hot end, and then move either your hot end around and up and down, or you can move the bed around or whatever, as long as you're creating some sort of either Cartesian or polar movement. And many of the parts are actually hollow, if you guys have ever seen printed parts, to save material and time, because it would take months to print solid parts in any large volume, at least the size these printers are. So, some of the key processes that affect the quality of an FDM printer would be, first and foremost, is layer height, actually, because you get independently fused layers, and if you say pick 1 millimeter as your layer height, you're going to see every single layer as you move up. And you'll also have bad adhesion, and it'll just kind of fall apart when you actually get it. Heating it is also another issue. So then I grouped a whole bunch of things into the words motion control, which I took as your XYZ movement speeds, how much you're extruding by moving. It's basically everything that goes into slicing and making sure that your printer moves properly in all dimensions. If you're out of square, you're going to have a really big issue with printing. And then nozzle diameter is another very influential machine parameter that actually will affect your part quality, because it changes the width of the bead that you're laying down as you're moving along. And then for specifically powder fills, the volume percent of filler changes the viscosity of your polymer a lot, and actually can make really brittle and cause the part to be. That printer's actually a Mendelmax 2. It's actually the one that we have in our lab right now. And typically when you're printing a filled polymer, you have to have the extruder on the x-axis or whatever axis. You can't use a Bowden system, which is what a lot of the newer printers use to save weight on your gantry. So then some of the niche processabilities would be, one of the newer ones is actually embedded, embedded electrical conductivity inside of your parts. Just recently, another newer one that actually somebody just put a Kickstarter up for is sinterable polymer stuff. So that just popped up like 20 days ago, and somebody wants to sinter these powder fills into fully dense parts, which is what my research is in. And then it's actually a really big enthusiast market, like I was saying, so it is its own niche by itself. Some of the materials that are used are your typical fused deposition materials, such as PLA, ABS, nylon, polyethylene, terephthalate, high-density polyethylene, and polycarbonate. Typically only PLA and ABS and sometimes PET are filled. These are all being tried because they all have different properties that will allow you to put different materials inside of them. PET can be used too, just really, really high temperature. So some of the fills that exist right now are a carbon fiber or a powdered graphite. Glass fiber is a really new one, actually, that I haven't even seen really outside of a still trying to get it to work research type feel. Pretty much any metal powder, such as iron, stainless steel, bronze, and copper. And then a wood fill, so they put sawdust into it. And then ceramics is also sort of a newer one that's just coming out. So this is one of the case studies. This car, I mean, I'm sure most people have seen this, the 3D printed electric car. It was a collaborative effort between Autodesk and a company called Local Motors. It was printed using a carbon fiber filled ABS to improve its strength slightly on a very large proprietary printer. And they're hoping to sell it for around 11,000 pounds with drivetrain and everything, but I don't know if I would trust its safety in a car accident. Um, and then, so one of the vendors of this filament is called Protopasta. They're actually just out of Vancouver. And they offer the stainless steel carbon fiber and a couple other uh, infills. And you can see they printed one of the little car models because it's actually a freeware. Or it's an open source project that they're letting basically anybody do. You can see that when you add powder to these polymers, you can actually polish them and make rings like that that are almost, they look like they're made of steel, but they don't even have the same mechanical properties as the plastic they're made with. They're much worse, typically, when it comes to powders. But then a carbon fiber fill, because it has the slightly longer strands, actually gets stronger when you add it. This is a hex copter frame. So this is an example, again, of the protopasta stuff. This is the carbon fiber. I don't know why it's so blue. So this is one of the difficulties that you run into a lot of times with the increased viscosity of powder fill, is that you get really crummy finishes on everything. Even though it's stronger and does kind of look cool, it's much harder to print. And this is an example of some of their conductive stuff. So this underneath here is their conductive filament, so that you can actually use it as a light. This is a video game controller, and then a stylus that actually works with a capacitive screen. They will erode your nozzle really fast, so you can typically only print up to about 20 hours straight of this stuff, and then your printer will need a new nozzle every time, at least with brass. And another example that is a little more recent is ColorFab is coming out with some of their new carbon fiber stuff. This is all printed besides the shocks and the shafts. This is an RC car rear end, and they're based out of the Netherlands, and they have similar products, Protopasta.